So we'll be talking about table encryption in Apache Iceberg. I'm Gideon Gershinsky, committer and PMC member in Apache Parquet. And I also work on big data security in Iceberg, Spark, Parquet, and some other projects. I also design and build data security solutions at Apple. But first and foremost, it's a community work, a community project. So we have the Apache Iceberg community working on this since 2021, basically. And special thanks go to Ryan for major contributions to everything, the design, coding, and review of table encryption. Many thanks to Russell, Yufei, Steven, DB, Gian, Jack, and Maya. Thank you. Okay, so the agenda for today's presentation will take a high-level view of what is the table encryption in Iceberg. We'll see how to write and read encrypted tables. I'll run a basic demo. Then we'll dive deeper into the details of Iceberg encryption. We will briefly discuss an interesting question of what are the performance effects of using encryption in Iceberg tables. And finally, we'll talk about the next steps in this project. Okay, so we talk about the data lake scenario. Obviously, we have this huge data storage in the middle, which keeps the big data, and we don't trust this storage backend. Data might be leaked from it. The data might be modified maliciously. That's why we encrypt the data before selling to this storage backend. So on the left side, we have the ingest part to the data lake, where we have a new application data or existing files or message streams coming to, for example, a Flink with Iceberg or Spark with Iceberg. And we encrypt the results data and put the encrypted files in the storage. On the right side, we have consumers of this data, notebook users, bad jobs. For example, it could be Iceberg with a Trino or Spark. And they take those encrypted files from the storage. They use a so-called key manager. And we'll talk a lot about the key manager in this presentation, so don't worry. This key manager helps us to open those encrypted files so we can process them. So the aim of this mechanism is to protect sensitive data at rest or data in storage. And by protection, we mean two things. One is to keep the data confidential, so we hide the sensitive information in the storage, and obviously we use encryption for that. But we have an additional goal: keep the data tamper-proof in the storage, so we protect the integrity of sensitive information in the storage, and we use crypto signatures and the unique module IDs. I will explain later what it means. What do we mean by the table data? All Iceberg table files in the storage. The data files, manifest list, metadata, and so on. So the result is Iceberg's built-in encryption engine. It's a native encryption and tamper-proofing mechanism implemented inside Iceberg libraries, which makes it cloud agnostic, obviously. It works exactly the same with any storage backend. It also allows to work with multiple storage backends in parallel if you want to, or to migrate sensitive tables from one storage to another. You just move the files. You don't need to decrypt, extract, encrypt the files. It also enables you to efficiently share sensitive tables. So no need to decrypt, extract, and encrypt a copy for each eligible user. Instead, you simply provide those users with access to the table key. And all of that, from the storage point of view, is client-side encryption. The data and encryption keys are not visible to the storage backend and its admins. Okay, so the main concept in Iceberg encryption is the table key. It's a master key that protects an Iceberg table. It is set per table, not per storage bucket or catalog. So it allows for quite fine-grained table access control. We call it table master key because it unlocks all of metadata and the data files in the table. So the identity of this key is just a table property. That's how we create an encrypted table. We just add a table property named encryption key ID. In this example, we call the key key A. So the table keys are stored in KMS, key management service. We'll talk about the details in a bit. And the KMS server verifies users' authorization to open the tables using key A in this example. And then it uses key A to decrypt a table metadata file key. We'll see what it means. And then we have a KMS client. That's a class that can talk to the KMS server. And the class path is considered as configured setup using the catalog properties. So let's see a quick demo how this works and looks like. So I have Spark 3.5 distribution, a standard one, but I've added a couple of Iceberg jars. And now I can run the Iceberg 101 demo shell. You'll notice that I have added a new configuration parameter with the KMS client class. Okay, so we started a shell which can write and read encrypted tables, but it doesn't have to. I mean, we can use the same shell to write regular tables. So if I just run standard create table operation and insert and select some data, this table is not encrypted because let's see the files. For example, we can find the data files and the metadata. If we just dump the content of those files, let's start with Parquet data files. We can see that the file starts with par1 magic string, which is magic string of Parquet files with unencrypted footer, plaintext footer. And we can actually see some of the contents of this file in plain view. so it's not encrypted. Let's dump the JSON metadata file. Again, fully visible, readable, it's not encrypted. Okay, I'll remove the temporary store and let's run the shell again. This time we will create a table with a table key. Again, how do we encrypt the data? We just insert it in this table. And to decrypt the data, we just select it from this table, so it is kind of transparent. How do we know that the data and table is indeed encrypted? We again dump the content. So, for example, if we try to open the JSON file, we will see that it starts with magic string AGS1. We'll talk about it in a minute. And the content is scrambled binaries, right? Not readable. Let's dump the Parquet file. It starts with par-e, which is a magic string for Parquet file with encrypted footer, and the content is again scrambled binary. Cannot be seen. That's how we know that files are encrypted. Okay, back to the presentation. The status of this work. So a disclaimer. It's still a work in progress, subject to changes. Many pull requests are already emerged, as you can see, but not all of them. We have a couple still under review, so keep that in mind. Also, the currently planned limitations for an initial MVP version, it is focused only on Spark writers and readers. So, for example, Flink and the Trino integration is still in progress. It will support initially only Parquet and Avro data formats, and not RC. There won't be per column keys in the tables, even with the Parquet data. So initially, we encrypt all columns with the same table key. And finally, we start with the Hive catalog. Other catalogs that use base metastore table operations should be easy to support. And also, obviously, the REST catalog is in the pipeline. We're working on it. Okay, diving deeper into details. You all know this chart of Iceberg file layers. So what we do, we encrypt each data file with its key. Then we put its key in the parent metadata layer in the manifest file. We encrypt the manifest file with the manifest key. Then we put the key in the manifest list. Now we encrypt the manifest list with its key. And here we have some changes. We probably encrypt the manifest list key before putting it inside the metadata files, because, for example, we don't have those files in the REST catalog. And if we have the metadata file, we encrypt it with the metadata key. And then we encrypt the metadata key with the table master key using the key manager. And put the result in the Iceberg catalog for this table. So it's a kind of envelope encryption, a standard practice in big data security, because data files are encrypted with data keys, and the data keys are encrypted with other keys. So we have envelopes in this picture. So the key management service is where your master keys should be kept in the production grade platform. If your organization doesn't have KMS today, you can use public cloud KMS Zero-Many, or you can install an open source KMS in your platform, or you can develop your own. Iceberg works with any KMS system, but it needs a KMS client to interact with the KMS server. So KMS client is a custom Java class that implements the Iceberg KMS client interface, and it is leveraged to encrypt and decrypt the metadata key, as we saw, with the table master key. So the client would handle authentication and authorization of the users in cooperation with the KMS server for your organization policies. You need to develop it just once, and then all users in your organization can use this class. This class implements the Iceberg key management client interface, which is simple. It has two basic methods. One is a rep key, where we give you the metadata key and the identity of the master key for this table. And then you need to go to your KMS system, ask it to encrypt the metadata key with this master key, and give us the result back in the return value. The unwrap is just the opposite of this. Here we give you the wrapped metadata key, what you gave us in the wrap key operation. So we give you back because we stored. And we also remind you the master key ID for this table. And we ask you to go to your KMS and unwrap or decrypt this key and give us the key back. There are a couple of mock examples of KMS clients. And in the future, we might provide clients for popular KMS systems. Okay, so let's go layer by layer to see how the encryption is done. So for data layer, if we use a per format, we leverage the per modular encryption. That's a standard part of the Apache per format since 2019. It encrypts and assigns all modules inside per files, pages, column indices, and so on. It preserves full per capabilities in encrypted files, so all of columnar projection, predicate pushdown, compression, and encoding are still possible. And it preserves the performance of analytic engines with encrypted files. We'll see why in a minute. How do we tamper-proof the data files in the per format? So we actually do two things here. One, we make sure that the content inside a file is not tampered with. For example, an attacker can replace one page of per with another page. We don't want that. And also we make sure that a file, whole file, is not replaced with another file, for example, from an old version of this table. For all of that, we use the standard AES-GCM cipher, authenticated encryption, which takes two input parameters. One is the encryption key, and another something called AAD, additional authenticated data. So each PRK module is signed using the module AAD, comprised of AAD prefix and AAD suffix. AAD prefix is the unique ID of the file, so the file cannot be replaced. The ID suffix is a unique module ID inside the file. So we end up with a unique string for this module. So that's it. When we send the key metadata for this file to the manifest, the key metadata will be comprised of the encryption key and the ID prefix for this file. What do we do with the Avro data format? It's not a columnar format, and it doesn't have a built-in encryption support. So we have designed a new mechanism for flat encryption of data streams, flat because there is no columnar structure. It is simpler than PRK encryption. We call it AES-GCM stream file format extension. You can read the spec. And it encrypts and tamper-proofs Avro data files, for example. It works by breaking data streams into blocks. Each block is encrypted and signed using the same AES-GCM cipher, taking two parameters. One is the file encryption key, and another is the AD, comprised of the unique file ID, the prefix, and the block sequence number, which becomes the AD suffix for this. And the file structure starts with a magic string, AGS1, followed by the block length, currently hard-coded to 1 megabyte. No reason to change for now. And followed by the sequence of the encrypted blocks. And again, the data file key metadata is comprised of the encryption key and AD prefix and stored in the manifest. We also store the data file length because it is required by AES-GCM stream. Okay, so now the manifest and the manifest list files, again, they are using Avro format, so we can encrypt and tamper-proof them using the AES-GCM streams. The manifest file key metadata is comprised of the manifest key and the AD prefix and stored in the manifest list. For the manifest list key, as I mentioned, we will likely encrypt it before storing using the metadata key because the metadata file and its encryption are all optional. Okay, and finally, the metadata file, they are in JSON format, but again, we can apply AES-GCM stream mechanism to encrypt and tamper-proof those files. Why would we want to encrypt the metadata file? For example, to hide the table schema. Sometimes it is considered to be sensitive information, so you might hide it if you want to. Now, the key of the metadata is wrapped or encrypted with the table master key in the KMS system, the key metadata for metadata file is comprised of the wrapped metadata key and ID prefix and stored in the catalog. Now, this key metadata doesn't expose the secret information because the key is wrapped, so we don't store plain keys in the catalogs. But still, we require catalogs to be protected against modifications or tampering to prevent, for example, key removal attacks or replay attacks, which should be fine in most catalogs, because in a catalog, server is typically independent of the data storage backend. It uses some database and its own service, so it's not affected by the storage. And to complete this picture, before I said that we store keys in the parent metadata, so now we know that we store basically three things for each file layer. We store the key, we store the ID prefix, and we store the file links. Okay, so what is the performance effect of encryption? Starting with the raw AES-GCM performance, this cipher is so standard and so popular, it is actually implemented in the CPU hardware. All modern CPUs support something called ASNI, the native interface. And Java supports ASNI in the hotspot engine for a long time now. So the result is encryption throughput in gigabytes per second in each thread in Java. It's probably orders of magnitude faster than input-output and the software stack. You have the application doing some work, you have the framework, you have compression, so it should be okay. So the file encryption in Iceberg, it's local. We encrypt the data files inside worker nodes. We encrypt other files inside the driver node. So all file encryption is local and fast. It's fast because it's first hardware accelerated. And second, both Parquet and IGS have a software optimization for encryption. They use the modular structure, so we never encrypt individual cell values in the table. It kills the throughput and the compression. So we only encrypt larger modules or blocks, which is fine because the module page is a minimal unit inside Parquet file. Now, in the Iceberg, we have an additional operation for table encryption, and that's the metadata key encryption. So we encrypt the metadata keys using the table master key, using a KMS service, which can be remote. That can be a remote operation, but this operation is performed once per metadata file read. It has a much lower frequency than data file read or manifest file read. Obviously, we use the efficient Iceberg metadata structure mechanism here. So what's the bottom line for Iceberg encryption performance? File encryption is local and fast. KMS interaction can be remote but infrequent. So we believe the encryption won't be your bottleneck. You have application workload, you have data input output, you have compression, and so on. And also we work on performance benchmarks for the details. Okay, what's next? That's the last slide. First is to complete the 2 remaining pull requests. So again, a disclaimer, it's work in progress. Then we will extend the MVP with the Flink and the Trino integration and also additional catalogs. We will run performance benchmarks. We will build the column encryption, meaning that in addition to a table key, you can have separate master keys for select columns. This way, you can build the per column access control, and obviously it will work in the tables with the Parquet data files, not in other data files. And we also want to support encryption of RC data files. RC supports encryption, but the challenge we have, it doesn't support integrity verification. It uses another cipher, so that would require some analysis. And I think with that, I'll stop and thank you and take questions.
All right, Gidon, thank you so much. We're going to open it up to any questions. Please use the chat function or the Q&A tab towards the right-hand side. We do have a few questions, Gidon, so I'm going to start from the bottom here. All right, so first and foremost, can you perhaps explain how key rotation is supported? That's the first part of the question. The second part of the question is, do we need to re-encrypt the entire part of the data when the key is rotated?
Okay, so key rotation is a big subject, and the simplest and the smallest part of key rotation is just to update the master key in the KMS. That's, I think, what is done in most of use cases. You just tell your KMS to create a new version of the master key, meaning that next time you write your data, your manifest and the manifest list and the metadata, all of them will be encrypted with a new version of the master key. So you have a fresh key, you have rotated your master key, and I think that should address the vast majority of threat models and use case analysis. It's kind of 90 to 10 situation. But if you want to go beyond the 90, and if you have a different threat model, then you can basically perform a heavier part of this operation, namely re-wrapping of your metadata files, manifest and the manifest list files, using this new rotation. So this way, basically, the data keys are not changed, but they are encrypted with a new version of the manifest keys, and the manifest keys encrypted with a new version of the manifest list keys, which in turn are encrypted with a new version of the master key. So if you call a kind of manifest rewrite action, that's what you get, right? Automatically. So again, the simple approach would be just to update your master key inside KMS, and all of key rotation is transparent to Iceberg. But you can also run manifest rewrite operation, and then you rewrap the data keys with the new keys. And in all cases, you never re-encrypt the data files. It's data. You don't want to touch the Parquet files or data files of other kind. You simply handle the metadata only.
Okay, great. We're roughly got about 6 minutes or so, so I'm just going to go ahead and go through them here. Does the Iceberg table encryption match FedRAMP requirements? And more generally, is Iceberg FedRAMP compliant?
Which requirement?
I'm not really sure. It was just a question that was dropped in here. I'm not sure if it's too vague, but it was anonymously sent. So if you did write that question,
I don't see it in the
it's
chat.
fine.
Okay, offline.
Well, yeah, we'll go ahead and move on here. Okay. Is it possible to implement differential privacy in Iceberg?
Yeah, that should be possible. We always look for new contributions, but that would be a big project.
Okay. All right. Is it transparent to different compute query engines?
It will be. So currently it is transparent to Spark.
Okay.
Engine, because from a Spark point of view, there is no encryption. It just works with table as usual. It's the catalog part of Iceberg that knows that the table is encrypted, and it manages encryption behind the scenes for Spark. But the Spark engine doesn't see anything. Once we integrate that with Flink and Trino, it will be the same for them.
Okay, all right. The next one is a two-part question here, Gidon. Does Iceberg support a certificate authority like KMS that could manage access to table keys over the shared access control model? And the second part to that question is, can keys rotate or expire on a schedule to limit access?
Okay, so it's a good question. I mean, the first part, because KMS is just a plug-in for Iceberg. So custom class, and you can implement anything. Anything that checks certificates, user authentication, authorization. So it's all up to the developer of this KMS client and plugin. The rotation, as I mentioned, it's mostly the KMS operation. It's a job of the KMS servers. But combined with manifest rewrite action, it can be completed on Iceberg part as well.
Okay. All right. Moving on to the next one here. Is the plan to allow use of different keys for different columns in the future?
Yes. So as I mentioned, we do plan to develop columnar encryption, which actually means that we will have additional master keys for a table. So today we have just one master key for a table. It's a table master key. But we will have column master keys. So you will be able to configure a certain subset of columns with different keys. It could be even a column specific key per column, any granularity. And that means that to project a column in your query, you will need two keys. One is the general table key, but in addition, for this particular highly sensitive column, you will need access or rights for the column master key.
Okay. All right. Thank you for that. Moving on to the next one here. What do you do with statistics information, including maximum, minimum, which might be sensitive information, which lands in manifest files, HMS, etc.?
Yes, so that's exactly the reason we encrypt everything. So as I showed in the slides, all Iceberg files encrypted, and we encrypt manifest and the manifest list files, especially in order to hide the stats.
Okay. All right, perfect. We're roughly got about 2 minutes here. So just like Avril Parquet, is it possible to implement Iceberg without catalog like Hive, Glue? so that those catalog limitations does not come with Iceberg?
Well, so for each catalog, we need to make some modifications to enable encryption. So as I mentioned, we start with a Hive metastore, and you can take this as an example. It's a few lines which are added, but we need to handle encryption explicitly inside the catalog.
Okay. All right. And last one, would per column statistics be encrypted with separate per column keys in the future?
Yes,
I believe I already asked this question. So.
No, that's a good question. It's a new one. It wasn't asked yet. But the reason for this separation, we could have started with a column encryption in the first MVP version, because Parquet already supports column encryption. But we needed to handle the Iceberg stats per column in Iceberg metadata. That's the reason we'll need an extra effort to enable this.
Okay, great. That's all the time we have. So thank you for joining us. Thank you, Gidon, for a great session.